500 millimeter per minute, that is the high speed, it is to eliminate the effect of time and temperature on these viscoelastic materials. So this is a way that being simulated to this design and this test value. In fact, all these test specimens and the way it is being tested, these are all the results of simulation. But as I mentioned that you can do it manually or it was designed manually, but when you have many parameters influencing your process, lot of things influencing the process during applications, etc., then you cannot do it manually or by hand. Then you have to go for computation. So nowadays, this simulation is being done with the help of a computer, with the help of a software, and that is what we call it as a computation technique. Now, if you consider the rubber product development, what is the classical way? First, we need to optimize the compound, then the process and design using prototypes, then functional property check. If everything is okay, you approve it. If it is unsatisfactory, then you have to again go back to the fault analysis, again redo it. So it involves a lot of steps and time consuming steps, and time is money, so a lot of money is also involved. Now, when you simulate virtually, that is when you go for computation, then what you are going to get, the process is of course cheaper. Now, software is costly, but running a software is not costly. So it's a one-time investment you can have. So it's cheaper, it is faster as well, it can be replicated multiple number of times. You can do it multiple number of times. It is safe since it does not require an actual disruption of the system. Nothing in practical you have to do, you are only going for computation with some data input. And it is ethical, of course. So this practice is ethical. Now, what is finite elementing? Finite elementing is basically a numerical technique for finding approximate solutions to boundary value problems for partial differential equations. Now, how this partial differential equation, this term or this concept comes? So when you have a design, suppose you have a design of a product, then what you do a hypermeshing of that. Means you have to divide that product virtually, of course, into very small meshes, right? And if you recollect your class 12 calculus, differential equation differentiation, what is differentiation? Is a division into a very small level, that dy dx when limit x that tends to 0, right? Means minimum, you can have that area or whatever, right? Dimension. So that way dy dx means that division, right? And when you have more number of variables, rather more than one variables, then it's a partial differential equation. So in place of dy dx, we used to write del y del x, right? So when you are handling many variables, after division, the cells that you have developed, then it becomes a partial differential equation. So that finite elementing means that when you are dividing your design into these very small cells or nodes, sometimes we used to call. So here, so here you see first you need to have a geometry, right? Means the product that you want to develop. So that product is developed, or the geometry is developed through that CAD, right? It's a very common thing now, CAD. With the help of a CAD, you can have the design of the product. Then you go for this hypermeshing, right? This is the hypermeshing, and this is the heart of the process, that you need to divide that product into very small, parts, right? And then you put these conditions, right? Boundary conditions, and then you simulate. Simulate means how the behavior of those parts will happen when there are external conditions being applied during the application of the product. And from there you will get the result and you analyze the result. Yeah, this is the block diagram you see. It starts with the 3D model building. Then you have to go for this 3D meshing, what we call it as a hypermeshing. Then you put this material property and the boundary conditions to that, go for this differential equation, solve, and then you get the data and you analyze it. Can you run this video? So I can demonstrate this with the movement of the earthworm, you see. Yeah. So here you see that if you want to simulate the movement of an earthworm, right? So how you do it? You see its body is constituted of so many small cells or parts, you can see. So this is what you need to develop, right? This is your product. This is your product. What you want, its movement. And for that, you see these are the cells that you need to divide your product in it, right? And you see the characteristics of the cells, right? They are periodically being extended and compressed, and because of that, the movement occurs. So when you have this entire product, when you divide it into these cells, that is hypermeshing, and the interconnection and I mean your relative properties between these cells helps the performance or working of this worm, right? So this is actually what we done in finite element simulation. Here you see that when you have a design of a tire and you want that how tire performs when it moves over a surface that is having a sharp object, right? So you see these are the meshes, right? These square meshes, right? So this design through hypermeshing you have developed these meshes, right? And when it comes over this sharp object, you can see the stress distribution. This color and there the stress values are given. Red colors, these are the highly stressed areas, right? And the blue colors, these are the least stressed areas, right? And if you have the material properties, a tensile strength, right? Tensile strength data of this compound, right? Trade compound, and if you see that how much stress is being developed there, so if you have the tensile strength value higher than that, it means that there will be nothing happening when your tire rolls over this kind of a sharp object. Now, why it is important for rubber products? Because we know that rubbers are highly reactive to stress because it gives a relaxation based nonlinear deformation. Obviously under dynamic stress because it gives the frequency based relaxation, heat dissipation, fatigue, etc. under dynamic condition. Then in strain gives the crystallization, heat generation due to entropy loss. Time, if you give time, then there will be creep and oxidation, and temperature effect because it changes the hardness, modulus, viscosity, oxidation. So many variables you can encounter, your product can encounter during its application, and this is a fit case, these rubber made products for this kind of simulation. Sorry. Now you see that if you want to account the performance of a rubber compound, you need the contributions from perfect compounding, perfect processing, and perfect design. So collectively all these will give you this performance, right? And through this simulation process, you can have a good idea of all of this so that a better or sometimes the best rubber product you can develop. So these virtual production processes, this can help to minimize the number of design cycles, troubleshoot product imperfections, and optimize equipment performance. So you will get an overall product development with this process. Simulation and optimization of the individual process as well, as I was mentioning that vulcanization. How do we do this curing study in ODR, MDR, whatever? We do the study at say 140 degree, 145, sometimes 160. We maintain that temperature for the entire period. So it becomes an isothermal process, but when you go for actual vulcanization, the process does not remain isothermal because your rubber is a bad conductor of it. If you put carbon black, the conductivity would increase, but it will never reach to the level of conductor. So the process never remains isothermal. So it becomes non-isothermal, right? So for particularly bigger size products, thicker products, so this non-isothermal behavior plays a very major role in assigning the properties. So you can also simulate that condition, that non-isothermal condition for vulcanization process itself. Then say for tires, the aerodynamic simulation can also be done. This technique can account for the effect of tire deflection due to a vehicle weight. Then also the product failure analysis can also be done using this simulation process. Now these are the general input variables for simulation, and this hyperelastic model is considered instead of viscoelastic in simulation of rubbers. Static mechanical properties, dynamic mechanical properties, temperature, and any other properties that fits the application that can be used as an input data. Now, what are the steps? First, you need to define the problem. Then you do the material characterization. Only few key data are required. So with the minimum R&D, you can execute the process. I will show. Then you create a geometry, that is the model using CAD. Then you do the hypermeshing, apply load and boundary conditions, because when you do the test, it means that you apply some stress in any form. It could be mechanical, thermal, anything, and you record the response. So that stress you apply and see how it is performing. Then select the appropriate analysis type, run the simulation, then do the post process, that is analysis, and if it complies, then it's fine. If not, then you repeat it, but that repetition can be done very fast. And regarding the boundary conditions, means what are the input variables that you need to give, and particularly for the design, where you need to fix the design and where you want to put the stress. So these are the boundary conditions you need to input. So this is the first case study. You see that vis-a-vis comparison between a simulated data and an experimental data findings. You see that the crack growth in a rubber part. So left hand side you see the simulated values, and right hand side the experimental values, and both are almost same, 30.7 milliseconds. After 30.7 milliseconds, the crack growth completes and the product fails. So simulated data and experimental data in just matched, and you see what minimum data you can give, that tensile and hardness. You don't have to make this product, you just develop the compound, find the tensile properties, measure the hardness, put them, simulate, and get the result. This is another one, this is our work. We tried to replace the rubber grade silica in bead compound of PCR with nanosilica, and then we simulated to check whether the nanosilica can reduce the heat generation or not. So this is the formulation, and we replace the rubber grade silica with nanosilica. 1, 2, 3, 4, and 8 you see this nanosilica and that rubber grade silica. Sorry, zinc oxide, sorry, extremely sorry, zinc oxide. And you see for this simulation, the data input was only dynamic modulus and Pine effect, tan delta, hardness, and specific heat. As you want to measure the temperature rise, then you need to put the specific heat data. So with that, we did the simulation, and you see that it shows the control compound, the temperature it can develop 108.7 degree, whereas the experimental compound with this nano zinc oxide 100.8 degrees. So almost 8 degree drop in temperature with nano zinc oxide in place of the rubber grade zinc oxide. That is being given by the simulation. Because you cannot make this one and check, instead of that we did the simulation and we checked. This is another one. Here I have given you this result along with the number of days it required to do, right, just to see that how fast you can do. So this is the work we done lately, that to do the performance analysis of an automobile bumper. We have not made it. Automobile bumper designed from 3D printed blends of polypropylene and SEEPS. SEEPS is generously donated by Curare, so we are grateful to them. So this thermoplastic elastomer we blended with polypropylene and tried to develop a compound and see that if a automobile bumper is made from that, then whether it would be more useful or beneficial than simple polypropylene or not. So you see that the day 1 we did the melt blending, day 2 we made the filament of it, Day 3, we just printed these dumbbells, right? And with these dumbbells, we measured the tensile properties on day 4, and we found that the 2 minutes only, I will finish. This 10 weight percent of SEEPS in polypropylene gave the good results, although we varied more composition. And here you see that we did that design, and the boundary condition is that in the two sides it was locked, and in the middle the stress was applied, and it was assumed that if that bumper is fitted and if undergoes a collision or it makes an accident, so we varied the vehicle speed at 40 kilometer per hour, 60 kilometers per hour, and we measured that how much deflection we can get. And here you can see the SEEPS modified, that is giving much higher deflection. It means that it will not break, right? And the data input were only tensile strength, tensile modulus at yield, elongation at break, and toughness. And we found that 45% of greater deflection we can obtain with this one. So these are the, your softwares which are available. Abacus is the most popular one, and otherwise specialized software is FED12, which is used for simulation. And these are the advantages. You can get the design optimization of your product, cost reduction for the development, improved product reliability, fatigue analysis, very important for dynamic application, comprehensive analysis. You can do overall complex geometry, you can analyze very, very efficiently the performance, and custom material models you can develop using this, that hyperelastic models, viscoelastic and creep models, etc., which are very important for the performance. And finally, I end with thanking Mr. Sareen for this invitation. Shomorda, Dr. Shomor, my senior, Malhotra ji, Kakkar ji, and of course, Rahul, my scholar, who does this simulation in my lab. And thank you for your patience hearing.
Thank you, Professor Bandyopadhyay. Any questions on this simulation topic? After lunchtime, it will be done. Okay?
Thank you, sir. May I request Mr. Subir Sen to present the memento to our speaker, Professor Abhijit Bandyopadhyay. Can we have a big round of applause? Thank you. Mr. Sen, please continue.
Professor Das, the next time slot is 20 minutes in place of 30 minutes. Dr. Das, distinguished academic and robust background with polymer technology. He earned BTech from University of Calcutta, PhD from MTech and PhD from Kharagpur in 1998 through 2002. Sorry. Dr. Das career spans prestigious institute worldwide, including position as postdoctoral researcher in Belgium, lecturer in Hiroshima University, then various other research role in various other institute, and now he is a visiting professor, associate professor, and now professor at Rubber Technology Center. His research focuses on innovative areas such as sustainable rubber compound, which is the talk of the town and the future of industry, nanocomposite synthesis, flexible sensor, and various polymer nanocomposite. Dr. Das has authored 175 papers, supervised 15 PhD, 11 master students, and guiding substantial research at IIT Kharagpur. Dr. Das has received multiple accolades, including Faculty Excellence Award from IIT, prestigious World Top 2% Scientist Award, and so on. Dr. Das would be speaking today about